we have emphasized in linear permutation that the objects should be distinct. But what if the objects are not distinct? For example, Roxanne has 3 vases of the same kind, 1, 2, 3, and 2 candle stands of the same kind, 1, 2. In how many ways can she arrange these items in a line? So, one arrangement that we can say is that if we're going to have, the candle stand here, and then this one. So we know that this is one change. Now, if I am going to interchange this vase with this one, is the change obvious? Well, no. Obviously, it's exactly the same thing. The vases are of the same thing. So when we interchange the vases themselves, it's like there's no use. It's just the same arrangement. This is the problem when we have repeating objects or objects that are not distinct. So how do we figure out how many arrangements we can do with this one if some arrangements are actually repeating? Now, we have 1, 2, 3, 4, 5 objects in total. So if we want to know all possible arrangements of them, that would be by the fundamental principle of counting and permutation, 5 factorial. However, from the 5 factorial, we need to remove the arrangements of the repeating objects. So when we remove something in factorial, that would usually be the division operation. Now, there are 3 repeating objects on the vase. So the number of ways of arranging these identical vases is 3 factorial. So I need to remove 3 factorial from 5 factorial. Now, the number of ways of arranging these 2 candlesticks would be 2 factorial. So I would also need to remove 2 factorial from 5 factorial after removing the 3 factorial also. So that's why they're here both in the denominator. And if you're going to combine that together, this will just be multiplication. So this is to say that if we want to find the permutation of these vases and candle stands, that means from the 5 factorial, which is the all possible arrangements of the 5 objects, let's remove the arrangements of the 3 vases because they're all identical, and the 2 candle stands because they're all identical. And in doing so, we arrive at the expression 5 factorial over 3 factorial times 2 factorial. And this will lead us to the value of 10. So, if you do not need to rearrange anymore the identicals, there will be 10 possible ways to distinctly rearrange the 5 objects. This is what we call the permutation of repeating objects. So the number of permutations of n objects of which n sub 1 are of one kind, n sub 2 are of a second kind, and so on, would be given by the permutation n factorial all over n sub 1 factorial times n sub 2 factorial, so on times n sub k factorial, which is what we illustrated a while ago. And again, this is called the permutation of repeating objects. So if we know that in our total list of objects we have a repeating object, then this is the one that we should be used in calculating. For example, the covered walk of a school is to be lined with flags. How many different arrangements of flags are there of the 10 flags if 5 are blue, 3 are red, and 2 are white? So if we just rearrange the blue, it will just look the same. So we will need to remove the arrangements of the 5 blue alone, the 3 red alone, and the 2 white alone. So therefore, by the formula of permutation of repeating objects, rearranging all of them is 10 factorial. From the 10 factorial, we remove the 5 factorial of arranging just the blue flags, the 3 factorial ways of arranging the red flags only, and the 2 factorial of arranging the white flags only. So therefore, your 10 factorial times 5 factorial times 2 factorial, this will give us 2000 rather, 2520 ways for our flags to be arranged. Now, let's take a look at the other problem. How many different 9-letter words can we form in the word committee, and the word may not mean anything? So, with this one, we know that in the word committee, there are 2 repeating M's, 2 repeating T's, and repeating M's, repeating T's, and repeating E's. So, with that, if we're going to solve this one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So therefore, the total possible arrangements of them will be 9 factorial. All over, let's remove the repeatings. Repeating M, that's 2 factorial. Repeating T, another 2 factorial. And repeating E, another 2 factorial. Which would give us 45,369 letter words that can be formed in the word committee, excluding the fact that we rearrange the repeating M's, repeating T's, and repeating E's. And these are examples of permutations of repeating objects.